Swayam Prabha. Digital India. Educated India.
Traffic stream characteristics. This is module 2.2. After completing this lesson, the student will be able to distinguish between interrupted and uninterrupted flow facilities, understand the characteristics of uninterrupted as well as interrupted traffic flows, understand the concept of passenger car equivalency, and identify various factors which are affecting the PCE values, passenger car equivalency values. First of all, traffic streams. How we define traffic streams? Where individual drivers and vehicles interact in unique ways with each other and also with elements of roadway environment. So, if we are talking about traffic streams, we have individual drivers and vehicles. They are interacting or they interact in unique ways with each other and also with the elements of roadway environment. Remember that dealing with traffic is entirely different from dealing with any physical phenomena. This is primarily due to the fact that you have human components involved in the overall process. There are drivers, they behave in different manners, not that each and every driver they behave exactly in the same manner. So, human component is involved and which makes traffic engineering different from any other or most of the other engineering discipline, or even it makes traffic engineering phenomena different from purely physical phenomena. We try to define traffic stream in quantitative terms. Quantitative term means essentially key parameters and their measurements. Basically, we try to do that to understand the inherent variability and define normal ranges of behavior. Carefully observe this statement, normal ranges of behavior. Just now I indicated that traffic is different from dealing with purely physical phenomena, because drivers they do not behave exactly in the same manner. But still, when we try to define traffic stream in terms of quantitative measures, key parameters and their measurements, we essentially try to tell or try to see the change as appropriate in the normal ranges of behavior. Maybe vehicles are moving at different speed, maybe let us consider speed as a parameter. So, then it is not that all drivers they will travel in the same speed, it is not possible. But you will find that most of the drivers they follow speed in a certain range. Now, if you improve the facility, widen the road, remove on-street parking, do some other corridor level improvement, you will find that still not all drivers will behave in the same manner, but the normal range of behavior, that is maybe the average stream speed which most of the drivers or the vehicles follow, that range might have changed and you will find probably a higher operating speed. For analysis, evaluation and also for justifying improvement, we need key parameters and their measurements based on normal ranges of behavior. Again and again, I would like to put emphasis on this particular aspect. We are trying to talk about normal ranges of behavior. We do not expect each and every vehicle to follow the same behavior or to produce the same behavior, but it is the normal range of behavior, and due to policy, due to other improvement measure, what is the change in the normal range in behavior. If there is a change in the normal range in behavior, we can relate it to the proposed policy or the activities. Now, with this background, let us try to understand traffic facilities. Two types of traffic facilities are normally there: uninterrupted traffic flow facilities and interrupted traffic flow facilities. You should carefully try to understand what is meant by uninterrupted flow facilities. Commonly by the term uninterrupted means we feel that every vehicle should move probably at a very high speed, and even if there is a speed reduction, even due to change in traffic volume, increase in traffic volume, we probably tend to interpret it as interrupted because traffic stream is interrupted, but actually the meaning is not so. So, you must be careful and understand how we define uninterrupted flow facilities and interrupted flow facilities. You must carefully understand the thing and the difference. In uninterrupted flow facilities, there is no external factors. Remember that we are talking about external factors. That is the basis for defining uninterrupted or interrupted flow facilities. In uninterrupted flow facilities, there is no external factor to cause periodic interruption to the traffic stream. Now, what could be the external factors? External factors could be traffic signals, could be stop or yield signs, could be uncontrolled access. Anywhere and everywhere vehicles are entering into the road and leaving the road, so that is creating disturbance. So, uninterrupted flow facilities, there is no external factor to cause periodic interruptions to the traffic streams. Still the internal factors remain. That means there may not be any traffic signal, may not be any uncontrolled access, but still as you increase traffic volume, based on the interactions among the vehicles within a traffic stream, there could be speed reduction, but still the facility will be considered as uninterrupted flow facility, because these are or there are no external factors like signals or access, uncontrolled access causing the traffic stream damage or reduction in speed, but it is due to the internal thing. So, even if the speed is reduced, does not matter what is the operating speed. For traffic volume is less, speed may be more, volume is more, speed may be less, but as long as there is no external factor to cause periodic interruption to the traffic stream, facility will be considered as uninterrupted facility. Now, such facilities include freeways and other limited access roads, where obviously you have perfect access control and no intersections or stopping of vehicle due to external reasons. Sometimes long section of rural highways also may operate as uninterrupted facilities. There might be signals, but those signals at very spaced at a very wide interval or large interval. So, in between two signals practically you have substantial length, there is no entry or exit of vehicles. So, you can find probably the facility is operating almost like an uninterrupted flow facility. Stream characteristics in case of uninterrupted flow facility depend on individual vehicles, also depend on the geometric and general environment of the roadway, but not on external factors, again to make it clear. Coming to interrupted flow facilities, this is the other one, just the opposite one, where traffic flow is periodically interrupted by external devices like traffic signal, stop or yield sign, uncontrolled access and so on. In this case, or for uninterrupted flow facilities, facilities are not available for continuous movement because there is periodic interruption. Vehicles do stop and start, signals vehicles periodically do stop and again they start. So, therefore, facility is not available for continuous movement, and remember that time enters as a significant parameter affecting traffic flow. So, time is a significant parameter that is entering in the overall process. We have to deal with traffic where constant stopping and restarting of traffic stream is very common because of this periodic interruption. Vehicle do stop and do start again. So, constant stopping and restarting. Then flow occurs in a platoon. This term is probably new to you. Platoon in generally means a bunch of vehicles moving together, a bunch of vehicles moving together. Just consider any signalized intersection. The moment signal is green, during the green period you will find one bunch of vehicle, they pass the intersection. Then again you have red, so no vehicle is passing. Again the green comes, signal becomes green, so again a bunch of vehicle passes. So there we call that vehicles are moving in platoon. If you want to define it properly, you can define it like this: a group of vehicles moving along a facility together with significant gaps between two successive groups. Significant gaps means once you have green, maybe a bunch of vehicle goes, then again red, so there is no vehicle, again green comes, again a bunch of vehicles. So, a group of vehicles moving along a facility together, and there are significant gaps between two successive groups. That is what is defined as platoon movement. Now, dispersion of platoon is an important consideration. Let us consider that the vehicles leaving an intersection, a bunch of vehicles leaving. The way they leave the intersection, if you start observing the vehicles at some distances from the intersection, you will find as the vehicle moves away from intersection, the platoon disperse. That means maybe the length or the distance between the first vehicle and the last vehicle in the platoon, that distance will increase, what we say a phenomena called platoon dispersion. And that is why, say, if there are signals which are closely spaced, you may observe still the facility may operate as uninterrupted flow facilities. But if there are signals on highways where you have generally access control and signals are placed at wide intervals, so there away from signal, if you operate the traffic, you will not observe it to be like platoons. So, you may find they are just moving without, it is not representing a platoon behavior, and almost it may operate at that point like uninterrupted flow facility. And that is why I indicated earlier also, signal spacing is also an important consideration. With this background, let us now try to see the traffic stream parameters. There are three macroscopic measures. You understand the word macro and micro. Why we say macroscopic measures? Because described by a single value of each, okay, which applies to the traffic stream as a whole. So, for the whole traffic stream, there is a single value, say macroscopic measures are speed, traffic volume, or flow and density. So, for the whole traffic stream, we try to define a single value of speed, a single value of flow and a single value of density, and that is why we call them as macroscopic measures. That means described by a single value of each, which applies to the whole traffic stream. There is also another parameter which is often used, rather which are oftenly used, because there are two types of headways, and we call headway as microscopic measure, because headway is applicable to individual pairs of vehicles within a traffic stream, not a single value for the whole traffic stream. Rather, it is between two vehicles. We define headway which is valid generally between two vehicles. So, they are called microscopic measures, but speed, flow and density are macroscopic measures defining traffic stream parameters. Now, let us see how do you define speed. Speed is normally the distance travelled in unit time. So, what is the distance that is travelled during the unit time? That is what we define the speed. It may vary widely over the route, not that every segment of the road drivers will enjoy the same speed. It is not possible probably, or it may vary at least often because of the change in roadway environment. Sometimes the width is changing, sometimes the abutting land use is changing, sometimes we find pedestrians are there, sometimes parking are there, and the combination of all this. So, the speed may vary along the length of the route. It may not be exactly the same for the complete route stretch, and it varies depending on the time also. At some time you may find it is taking, a road section is taking 10 minutes. At peak hour, the same road section it may take 20 minutes, 30 minutes. Okay. So, all these factors are there. Now, two types of speed measurement we normally use in traffic engineering. One is the time mean speed and another is the space mean speed. These are very important again. Time mean speed is often called as spot speed. So, we call it as TMS, time mean speed or spot speed. Another is the space mean speed, commonly referred to as SMS, space mean speed. Now, time mean speed is the average speed at one point or location over a period of time. It is carefully observed, it time mean. That means, we are averaging it over a time, at a place over a time. So, it is measured at a point or at a fixed location, and it is measured over a period of time, and we take the average of that. So, it is average speed at one point or location over a period of time. You will see that it is arithmetic mean of the speed observed at a point. Now, space mean speed is the average speed of vehicles over a certain length of road at any time. It is averaged over the distance. That is why it is called space mean speed. If you take a distance, what is the average speed that can describe the travel over this distance? So, it is averaged over distance. That is why you call it as space mean speed. We can show that space mean speed is the harmonic mean of speed observed at a point. We shall show it with an example also. Remember that space mean speed is always less than equal to time mean speed. Always it is less than equal to time mean speed. We can show it also. We shall show it with an example. Let us take an example. Let us consider that there are three cars moving with a speed of 20 km per hour, 40 km per hour and 60 km per hour, and traversing a length of d. So, at any point, let us consider they are travelling at uniform speed. 20 km means first vehicle is travelling 20 km per hour uniform speed over the length d. Second vehicle is travelling at 40 km per hour uniform speed over the length d, and so on. Therefore, at a point D, what is the time mean speed? We have observed 3 vehicles, one is travelling at 20 kmph, another is 40 kmph and another is 60 kmph. So, it is time mean speed ut is nothing but 20 plus 40 plus 60 by 3, so 40 kilometer per hour. So, it is nothing but if ui is the speed of vehicle I, then it is sum over ui where I equal to 1 to n divided by the number of vehicles n. That way we can write. So, this expression hold goes. So, it is the arithmetic mean of speeds, that is what we have told. Please let us refer back to this thing. It is the arithmetic mean of the speed observed at a point. So, that is what we have shown. It is arithmetic mean of the speed observed at a point. Now, each vehicle is travelling a distance d. So, what is the average travel time? First vehicle takes time d by 20, second vehicle takes time d by 40, third vehicle takes d by 60. So, what is the average travel time? 1 by 3, because we have observed 3 number of vehicles. So, it is essentially 1 by n sum over d by ui. Ui is the same speed 20, 40, 60, right. So, it is 1 by n sum over d by ui and I varies from 1 to n. So, what is the space mean speed? Space mean speed distance is d and it is covered at t bar time. So, d by t bar, which is nothing but d by 1 by n sum over d by ui. So, what you get? You essentially get it like this: 1 by n sum over 1 by ui, where I equal to 1 to n. N is the number of vehicles, and in this case you calculate it as 32.7 kilometer. So, now what we indicated, we told that space mean speed, it is the harmonic mean of speed observed at a point. That is what we have shown here. It is the harmonic mean of speed observed at a point. We have observed speed at a point is ui. So, it is the harmonic mean 1 by n sum over 1 by ui, I varies from 1 to n. Here also you can see that time mean speed is 40 kilometer per hour, space mean speed is 32.7 kilometer per hour. So, you can find space mean speed is lesser than time mean speed. It is always so. At best it may be equal. I leave it to you to think where these two speeds could be equal, when it will be TMS equal to SMS. Just think this part. Relationships do exist between the time mean speed and the space mean speed. Sometimes you might have measurements of the time mean speed for different vehicles, and sometimes you may have the space mean speed, observed space mean speed also. So, if we know one, that means if we know the individual time mean speed and mean and the variance, then we can calculate the space mean speed. If we know the space mean speed, again the mean and the variance, we can calculate the time mean speed. The following two relationship may be used. If this is the, let us consider this the variance of mean with respect to the space mean speed and with respect to the time mean speed, then you can use these two relationship. If you know the mean and the variance of the space mean speed, you can calculate the time mean speed. If you know the mean and the variance of this is the variance of the time mean speed, you can calculate the space mean speed, right. So, these two equations one can remember, and to get time mean speed when the space mean speed and its variance is known, and other way also, if you know the time mean speed and its variance, you can calculate the space mean speed. Now, other types of speed also sometimes we refer. One we call it as running speed, and another we use sometimes, that is journey speed. Now, running speed is the average speed maintained by a vehicle over a given length while the vehicle is in motion. This is interesting. Carefully observe that. while the vehicle is in motion. That means you exclude stop delay. So, when the vehicle is traveling from A to B, if you have the total time and then if you know what is the stop delay, total time minus stop delay, that is the running time. So, length by the running time, you get the running speed. So, running speed is length by the divided by the running time. Running time is the journey time minus delay. Journey time is the total time taken to travel these 2 points, defining this particular length. Journey time minus delay. Journey speed on the other hand does not leave this delay component. It is the effective speed of a vehicle between 2 points and it includes all delays incurred en route. So, it is the length divided by total journey time, not the running time. In this case, it was running time. So, it is running speed. It is the journey time including all the delays. So, it is the journey speed. That is what. So, often time means speed, we use time means speed, we use space means speed, and sometimes we also use running speed, refer to a running speed and also the journey speed. Now, traffic volume we measure normally in terms of number of vehicles passing a particular point of roadway during unit time, and traffic volume is normally expressed in terms of vehicles per hour or vehicles per day. We express traffic volume in terms of daily volumes, which is normally used in highway planning. Two types of normally measurements we used for representing the daily volume. One is called the ADT, commonly known as ADT, that is the average daily traffic, which considers generally the day to day variation, say within a week. So, we take traffic measurement for 7 days and take the average of that. So, we do consider the variation of traffic within a week. And then there is another measurements of daily volume, that is known as annual average daily traffic or AADT, annual average daily traffic. So, if we measure the traffic volume over a year, all the 365 days, maybe you have permanent count station, you can get traffic volume throughout the year. So, if you take the yearly traffic 365 days divided by 365, then also we get daily traffic, and that is annual average daily traffic, AADT, when we take the measurement for 365 days. And this traffic volume even takes into consideration the seasonal variation of traffic. Sometimes we find traffic may be more in winter, less maybe during the rainy season, moderate maybe during the summer. So, all sorts of seasonal variations are also reflected in terms of ADT or ADT measurement, but ADT do not reflect the change of traffic from one season to another. We also express traffic volume in terms of hourly volume, and this is normally used for capacity analysis. This normally reflects hourly traffic variation within a day. So, you may find that maybe during the peak hours from 9 to 10 in the morning and maybe again 5 to 6 o'clock in the evening, you have heavy traffic. So, we can use that type of measurement for capacity analysis. Sometimes we express traffic volume in terms of directional design hourly volume. Design hourly volume is fine, then added thing is the directional part, because both directions, if there is traffic is not balanced, then sometimes we use it for control measures, for safety analysis, and also for capacity analysis sometimes we use it. So, DDHV, directional design hourly volume, is expressed by ADT multiplied by K multiplied by D, where K is the proportion of daily traffic occurring during the peak hour. So, ADT is the daily traffic, how much percentage of that is occurring during the peak hour, that is expressed as K factor. It is normally or typically the 30th highest hourly volume. We shall make elaborate discussion about this K factor or 30th highest hourly volume later in some other lesson, and D is the directional distribution factor. Sometimes we even see the sub hourly volumes, because variation within a given hour may be important, because you may find the facility may have the capacity which is adequate to serve the peak hour demand, but short term peaks of flow within the peak hour may exceed the capacity. So, therefore, we may need to look at the sub-hourly volume also. There, in that context, we use this peak hour factor. Peak hour factor is nothing but hourly volume. You take measurements for an hour and then maximum flow rate normally based on 15-minute traffic count. So, peak hour flow is hourly volume what you have really observed over 1 hour, and then take peak 15-minute traffic volume, multiply it by 4, that means maximum flow rate based on 15-minute traffic flow, and therefore, you can get what is the peak hour factor. You will see often in signal design we will use this peak hour factor. When peak hour factor is known, sometimes maybe you have already studied some of the intersections and you know the peak hour factor. So, then that may be used to convert a peak hour volume to an estimated peak sub-hourly volume. It is just reverse. So, in that case peak hour factor is known, hourly volume is known. So, you calculate maximum flow rate, it is nothing but hourly volume divided by the peak hour factor. So, that way one can calculate the peak hourly volume. All these are necessary because this kind of short variation or variation of traffic flow within an hour also, that becomes important, particularly when you go for the signal design. So, there it is really meaningful. Now, the density, the third measurement, macroscopic measurements, it is basically the number of vehicles occupying a unit length of the roadway at a given instant. It is usually expressed as vehicles per hour, how many vehicles per kilometer, not per hour. So, over a length, take 1 kilometer road, how many vehicles are there? So, n vehicles per kilometer, that is what is the density. It is difficult to measure directly. So, often we calculate it indirectly using this relationship, density equal to flow by specimen speed. So, if we know the traffic stream flow and traffic stream specimen speed, we can calculate the density. We shall prove this relationship also. We shall show you the derivation. The density we often refer to as jam density. Jam density is the highest density occurs obviously when it will occur in the worst affected hours, peak hour, when the congestion is severe. You have vehicles bumper to bumper. Okay? So, that is the maximum density that can occur. So, we call it as jam density. So, jam density is the highest density when vehicles are standstill, that is the jam condition, and in this case traffic volume approaches to 0. Why traffic volume approaches to 0? Because you will find that vehicles are almost standstill, that is the level of density. So, obviously, because they are so much packed, the speed or the flow has virtually come down to 0. So, during the jam hour also, if you try to measure how many vehicles are crossing at a particular location, you will get almost nil or very little number. Now, the other microscopic measure headway. Here 2 types of headway measurement we do. Sometimes we call it time headway and space headway. Sometimes space headway is often referred to as spacing. Headway means, time headway means the time gap between 2 vehicles, passing of 2 vehicles. Space headway spacing means, space headway is the distance between the fronts of successive vehicles. So, space headway we are referring to as distance between fronts of successive vehicles. So, if you have density is k, so you have k vehicles per kilometer. So, what is the average spacing? 1000 meter by k. So, this is in meter, that is the spacing. Now, let us, you have this relationship q equal to k into Vs. So, that means flow equal to speed into density. So, speed you can again express in terms of flow and you replace this k by 1000 by s. So, you can get this relationship. Similarly, the time headway is the time interval between the passage of the fronts of successive vehicles at a specified point. It is measured in second. So, time headway is measured in meter and space headway is measured in second. It is reflected with space headway. It may be related to the space headway as follows, using this simple flow equal to speed, that is the space spin speed into density. So, using that basic relationship, you can relate the time headway and space headway with this relationship. Space headway equal to time headway by 3600 into space spin speed into 1000. That is what is the basic relationship. It is simple. You can derive this relationship using the basic fundamental relation, that is flow equal to speed into density. Coming to the characteristics of uninterrupted flow, we have already told that for uninterrupted flow it is flow equal to speed into density. So, we can try to show you that derivation. Let us consider 1 kilometer road on which all vehicles are travelling at the same speed. This is just for assumption to show you the simple formulation. The parameters k, q and v are concentration in vehicle per kilometer. Q represents flow in vehicle per hour and v represent the space mean speed in kilometer per hour. So, you have practically 1 kilometer length of the road, that is what we have tried to show. The density is k, so you have k number of vehicles, this is the first vehicle, second vehicle, third vehicle, like that, and this is the kth vehicle because density is k. If you measure the flow here, you will find per hour q number of vehicles are going, each with a speed of v kilometer per hour. Now, by definition, there are k vehicles, each with speed v kilometer per hour in 1 kilometer of road at any instant. That is what will define speed, flow and density. If flow is recorded at the end of 1 kilometer, you will observe probably q vehicles per hour. Now, let us consider a vehicle at the start of 1 kilometer. How much time it will take? Speed is v kilometer per hour. So, to cover 1 kilometer, how much time a vehicle will take? Obviously, it is 1 by v hour. Again, you have k vehicle, because the density is k, you have k vehicles spaced over a length of 1 kilometer. So, how much the kth vehicle will take? First vehicle will take 1 by q hour, second vehicle will take 2 by q hour to reach to that point. So, kth vehicle, how much time it will take? It will take k by q hour. And how much distance it is covering? You have k vehicles in 1 kilometer. So, essentially in k by q hour also it is covering 1 kilometer. So, therefore, one way we find that a vehicle will take 1 by v hour to reach at the end, and kth vehicle will also take k by q hour to reach to the end. So, therefore, 1 by v equal to k by q, and here you find q equal to flow equal to speed, space mean speed multiplied by the density. So, that way one can show this relationship. Now, several analysts have attempted to fit relationship to observed data of speed and density. It is not only for speed and density, they have tried to observe the relationship between speed and density, speed and flow, and then flow and density. Okay. So, we are trying to show some of the speed density relationship. The most popular one is the linear relationship between the speed and the density, and this is given by Green-Schiltz. So, this is popularly known as Green-Schiltz model. Here you can see I have shown the linear relationship with a graph. This way it is density is increasing, the speed is increasing in this way. So, when you have density 0, there is very few vehicle, the speed is maximum, that is the free speed or the free flow speed, and as density increases, the speed will come down because more vehicles are there. So, the interaction among the vehicles, there will be loss in freedom of movement and the speed will come down. So, finally, you will find when there is jam density, jam packed, vehicles are totally packed, then the speed is 0, and this is following a linear relationships given by this equation 1. So, Kj is constant because the damage density for a given road section, it is constant. Vf is the free flow speed is also constant. So, Vs equal to Vf minus Vf by Kj, all are constant, multiplied by K. So, this is essentially a linear relationship. Now, what will be the speed flow relationship and flow density relationship based on the above mentioned speed density relationship? Again, use that basic relationship, flow equal to speed into density. So, using that we can show that Q equal to Vf into K. Now, what is K? K is, here you can find Vs by Vf minus Vf by Kj. So, if you show this relationship, you can get equation 2 to represent the relation between flow and the density K, that is the corresponding flow density relationship. Similarly, you can show what is the relationship between flow and the speed represented by Vs. So, once you know any one of this relationship, in this case we have started with the relationship between speed and density. Once we know the relationship between speed and density, and then we know this basic equation, flow equal to speed into density. So, we can calculate or we can derive the relationship between flow and density and also the flow and speed, and those are plotted here. You can see, consider any speed flow curve, you have two domains. The upper part represents the almost stable operation where the speed is maximum here. As you are increasing the traffic volume, flow is increasing. So, the speed is coming down, and you have a lower part which is often denoted as the shown as the dotted line, because this is the unstable operation. We will have more discussion about the relationships later. But obviously, if you try to plot equation 2, you will get like this Q and K relationship like this, and if you plot this equation 3 Q and Vs, you will get this kind of relationship. So, here also you have two domains, here also you find there are two domains. Now, how to obtain the density when the flow is maximum? It is very simple, you can get it easily. When from the above relationship you can find the flow and density. When density is maximum, a flow is maximum, that time, that means dq dk is 0. So, take the derivative, dq dk is 0. If you put that, you will find density at capacity. If we define it as Km, density as capacity, is nothing but Kj by 2. Similarly, take what is the speed at density at capacity or the maximum flow. Again, you take the derivative dq with respect to V. So, dq dV, earlier case, what is the density at capacity flow? You get dq dk equal to 0. In this case, again you take the derivative dq dV equal to 0, and you find Vm, the speed at capacity, okay, or maximum flow, is Vf by 2, simple derivation. And that way you can find Q equal to again speed into density. So, flow at maximum flow equal to speed at maximum flow multiplied by density at maximum flow. So, you find it is essentially Vf into Kj by 4. So, if the linear relationship holds good, then we can show that the maximum flow can be expressed as Vf into Kj by 4, where Vf is the free flow speed and Kj is the jam density. Now, there are other relationships like Greenberg's logarithm relationships, Underwood's model. Okay. There are a number of relationships that have been developed by researchers over a period of time. Some of the relationship I have shown here. This is the Greenberg's model, is a logarithmic model is shown here. You can clearly see from this equation that this equation breaks down at low concentration when k equal to 0. If you put k equal to 0, it breaks down the relationship. Similarly, this under roots exponential relationship, it does not represent 0 speed at high concentration. Whatever may be the value of k, it does not represent exactly 0 speed as it was represented by Green-Schell's linear model. There are so many other models. You can refer to any textbook also if you are interested to know about other types of model. Now, coming to the characteristics of interrupted flow, here vehicles move in platoon and traffic signal is a major cause. So, let us consider a signalized intersection. Traffic is periodically stopped and then permitted to proceed. It is done basically to maximize the efficiency and safety through sharing of time for different conflicting movements. We want that the same space it is shared for different conflicting movements. So, we separate the conflicting movements by time. We allow some movements to take place at certain time, then we stop those movements, put red to those approaches, and then we allow other movements to occur. So, that way we try to maximize efficiency and safety at the same time. So, here headway already you know the time gap between passage of two vehicles. So, here once you consider a signalized intersection, the constant headway achieved with a stable moving queue, carefully observed stable moving flow, is known as saturation headway. So, earlier we told what is headway, now we defined saturation headway. So, what is saturation headway? The constant headway achieved with a stable moving queue. Initially the moment signal becomes green, initially a few vehicles may take a much longer time, and then after some time you will find that queue will stabilize. So, it will move at almost at uniform rate. So, there with stable moving queue, what constant headway you get is known as saturation headway. Now, obviously after green signal is shown, first few vehicles consume more than h, where h is the saturation headway. They consume more than h because of driver's reaction time to green signal. So, if incremental headways are added, that means above h for the first few vehicles, what are the extra time over h? If we add all of them, then that is known as start of lost time. So, carefully observe this terminology. So, if incremental headway above h are added for the first few vehicles, then a single value we can get what is known as start of lost time. That is what is shown here. Okay. This is the signal, vehicles are stopped here. So, once you give green signal, the vehicles start moving. So, you find that initially first few vehicles the headways are more, that is what is indicated here, but gradually it is coming down, and beyond certain vehicles you find that everybody, because here the stable queue movement has occurred. So, you find everybody is taking h amount of time, passage of two vehicles h. So, this h is the saturation headway. Now, if you take the first few vehicles, this vehicle let us consider, if this is the ith vehicle, how much extra time it has taken? It has taken this much extra time. If we denote it as Ti, then start of lost time is sum over Ti I equal to 1 to n. Even if you make it n, it gives you the same result, because for all these vehicles there is practically this Ti is 0. So, if you take the first few vehicles, you take the total start of lost time. That is what is shown here. Now, there is also a clearance lost time or end lost time, that is defined as time between the last vehicle from one approach, just it becomes red. So, the last vehicle between one approach entering to the intersection and the initiation of green signal for conflicting movement. One approach you are just making red, so the last vehicle goes, another approach you are leaving making it green, but you want to keep certain minimum gap, so that the last vehicle can cross the intersection area safely before another vehicle from another approach comes to that intersection getting the green signal. So, that lost time is basically known as clearance lost time or end lost time and denoted as L2. Okay. So, this total lost time is L1 plus L2 in the initial period and towards the end. Then saturation flow rate, you can calculate it. If you know the saturation headway, then each two vehicles, passage of two vehicle takes h. So, it is basically 3600 by h. So, if you know the saturation headway, you can easily find what is the flow corresponding to saturation headway. So, the number of vehicles that could enter the intersection in a single lane, if the signal were always green for that lane, that means a stable condition exists and vehicles were never stopped. So, that is what gives you saturation flow. Again, this is important if you go for the design of signal. Now, flow at a stop or yield signs, that also may be part of this uninterrupted flow facility. So, drivers select a gap in the major street traffic to execute the desired maneuver, and gap availability is accepted by the total volume on the major streets, its directional distribution and the number of lanes. Okay. Now, sometimes in for interrupted flow facilities, measures such as speed or density are not sufficient to fully describe the quality of flow or service provided by the facility. So, we use different forms of delay, stop delay, maybe amount of time the vehicle stopped while traversing a roadway segment, what is the stop delay, what is the travel time delay, we take a reference of the desired travel time, maybe that is what we expect or is desirable considering a high speed, and then whatever actual time the vehicle has taken. So, if you take the difference, you get the travel time delay. Sometimes we represent it by the approach delay, that means while vehicles are approaching an intersection, what is the total approach delay? It is used particularly as signalized intersection. So, it includes stop delays at the intersection plus the time lost in decelerating to a stop and then accelerating back to ambient speed. So, as if there is no stopping, then what would have been the time, and now because of deceleration, stop and acceleration, what time is taking. Now, coming to the concept of passenger car equivalency, you have seen we have most of the developing countries, we have mixed traffic operation. So, if you say the number of vehicles 100 vehicles, it is incomplete because 100 cars, 100 buses, 100 two-wheelers, they are all different, or maybe a mixture of all this, maybe they are all different. So, therefore, this concept of passenger car equivalency is introduced. Highway Capacity Manual defines passenger car equivalency as the number of passenger cars that are displaced by a single heavy vehicle of a particular type under prevailing roadway traffic and control conditions. So, PCE or passenger car equivalency in India, we often call it as passenger car unit, is also defined as the number of passenger cars having the same impedance effect as a vehicle of a given type under prevailing roadway traffic and control condition. The way a truck affects, if I try to see it is equivalent to how many traffic, how many cars, then that will again depend on what is the roadway condition, what is the control condition. With in presence of pedestrian, in absence of pedestrian, you have some parking, you have some other kinds of encroachment, roadside activity, all these will affect the equivalency. Therefore, PC is always defined with respect to prevailing roadway traffic and control condition. Remember that PC is influenced by all these factors, a large number of factors, we will quickly indicate them also. So, equivalency, if we say one truck equivalent to how many cars, or one bus equivalent to how many cars, it depends on a large number of factors. It depends on what is the roadway, what is the environment, what is the control condition, what is the proportion of other vehicle types in the street, what is the traffic volume, a large number of factors. So, PCE or the PCU is not really a static quantity, it is essentially dynamic. But till now we do not have norms for dynamic passenger car equivalency. So, what has been done, different static PCU values have been suggested for different roadway facilities, urban area, rural area, again urban maybe intersection area, mid block area which is free from intersections, like that for different facilities different set of static PCU values have been suggested, but truly PCU is a dynamic quantity. Let us quickly see the factors which are affecting the passenger car equivalency. Vehicle characteristics like dimension, speed, power, braking characteristics, etc. Then you have transverse and longitudinal gaps that again affect the PCE. So, basically it is there again a function of speed, driver characteristics, etc. So, transverse and longitudinal gaps. Then the traffic composition, what are the different vehicle types, what is the speed distribution, what is the traffic volume as compared to capacity, all this will affect the PCE, just to justify that PCE is really not a static quantity. Then it also depends on the roadway characteristics like gradient, curves. You have a steep gradient, the way the truck movement will affect the overall stream. If you have no grade, it is a level ground, the effect will be different. So, it depends on the grade, it depends on the curve. You provide a sharp curve and then some commercial vehicles like trucks, the scenario will be different again. So, therefore, whether what level of access control is there, whether it is rural or urban area, presence of intersection, even the type of intersection, all these are going to affect the PCE. You have traffic control and regulation, that also may affect passenger car equivalency, because whether it is one-way traffic or two-way traffic, whether they have posted speed limit, what are the different control devices you have en route, and also it will get affected by environmental and climatic condition. So, you know there are a large number of factors which affect this passenger car equivalency. Here I have shown some typical values of passenger car equivalency for Indian rural roads. You can find with respect to car we define, because we say passenger car equivalency. So, equivalency with respect to car, so car is 1, bus, truck is normally 3, motorcycles we have 0.5, cycle rickshaw 1.5, and then I have indicated also higher PCU values for some of the non-motorized vehicle. But these are just indicative and typical. You have a number of PCU sets for different types of facilities. Now, let me ask you some of the questions. Define uninterrupted flow facilities. Mention traffic stream parameters for uninterrupted flow facilities. Question 2. What is the difference between the time mean speed and space mean speed? State the relationship between the time mean speed and the space mean speed. Define passenger car equivalency and mention the factors affecting the PCU values, so that for Ginshild's linear speed density relationship, capacity flow may be expressed as Vf into Kj by 4, where Vf is the free flow speed and Kj is the dam density. A quick look at the answers to the questions of lesson 2.1. Why it is meaningful to attempt to influence the travel demand, discuss different ways of influencing the travel demand. Most of the cases you find demand is more than the capacity only for certain hours. So, rather than increasing the capacity, is better to see if we can distribute the demand over a period where even for a small period the demand is more than the capacity. Can we, instead of adding the capacity or enhancing the capacity, can we redistribute the demand and manage with the existing capacity? So, there are different ways: shift the temporal distribution of the demand, reduce the magnitude of the demand, or even go for the repackaging of demand. Explain the necessities for measuring the performance of transportation system. There are so many reasons we need to measure the performance: for assessing the existing condition, evaluating alternative improvements, quantifying associated costs and benefit, and for communicating the results to both technical and non-technical audiences. Explain your understanding about transportation system management, application of methods and procedures for increasing the efficiency, and objective is basically from high capital incentive approach to low cost, more rapidly implementable projects. These are the major components of traffic system. Thank you.